Hello everyone, my name is Andrew Birk. This is my research partner, Stephen Frank. We did our capstone research project, that was a graduation requirement in December, on the potential use of graphene as a shielding material in positron emission tomography. We're happy to report that we'll be reporting this research at the national conference in Denver, Colorado in June as well. So learning objectives before we get into the presentation. We want you guys to recognize graphene aerogel and its potentials. We want you to interpret the steps taken to conduct the research, verify the results of the research, and finally evaluate the potential application of graphene aerogel in positron emission tomography.
All right, so introduction. You might be asking yourself, what the heck is graphene aerogel at this point? Graphene is a newly created substance. It is marketed as the strongest and lightest material ever on Earth. Its ability to attenuate gamma rays is unknown at this time of our research. What's important in nuclear medicine is a little bit of physics. So we're going to take you back to alpha, beta, and gamma rays. We use the gammas to image the inside of patients. The gamma rays that also image patients is also what's going to give us some exposure to radiation. Currently, PET facilities use lead, concrete, tungsten for shielding. They also use carbon fiber and plastics on the machines, on the imaging scanners. Our research goal was to test the capabilities of graphene aerogel and calculate an attenuation coefficient just to see how well this will block gamma rays.
So our materials and methods that we use to conduct the research, we use technetium-99m and F-18 FDG radionuclides. These are radionuclides that you would see in any nuclear medicine facility to image patients. We use a Siemens Symbia gamma camera with a low-energy, high-resolution collimator at the Cleveland Clinic in Cleveland, Ohio. The attenuation materials that we tested were 25 millimeters of graphene aerogel, 10 millimeters of lead, 20 millimeters of lead, 17 millimeters of tungsten, 10 millimeters of copper, 10 millimeters of aluminum, and 2.2 millimeters of carbon fiber. 7 trials were conducted, 10 images per trial, and they were 1-minute images.
Okay, what you see on the screen right here is what you typically would see on a scan of a patient. You typically see like a brain, or you'd see a liver. What we did was we tested our materials, our lead, our tungsten, and you can clearly see the red being hot spots, many counts, much radiation, the blue being less radiation, and then the cold spots where no radiation was registered by the machine.
So you guys can see here, well maybe you guys can't see here, this is each trial and the material listed. So you can see 20 millimeters of lead. There's not too much going on in the center of the screen, whereas in an open study you can see that the focal point is very centered and there's a lot of radiation in the middle of that screen. So just based off of that, without the numbers, you're able to tell that 20 millimeters of lead blocks gamma rays or FDG PET radionuclides pretty well. So this is a visual representation of our actual setup. So this is our Siemens Symbia gamma camera. The bottom detector wasn't working at the time. We turned that off. So what we used was a PET pig, positron emission tomography pig. So what we do is they hold the radioactive sources in there to prevent the rays from getting out before they're administered to the patient. So that being said, we opened the top of it. There was a little hole in the top, and we were able to collimate our rays up towards detector 1. So those are the circles that you saw. So we weren't getting scatter radiation coming out of the sides and affecting the results. All of this was standardized. You can see on our P-scope or our positioning scope up there that they would use in diagnostic nuclear medicine to position for scans. You can see the focal point, the area of white is the area of activity.
Okay, materials and methods. This is a graphic representation of the picture you just saw. So you get to repeat our repetitions. We did the same every time. The dimensions, the detectors were set at the same exact settings, and that was repeated for each one of our trials.
So that just standardized our results. We're getting the same numbers because it's the same distance away.
We're very focused on counts. It has to do with counts. How many gamma rays are going to strike that detector, and this has to be the same every time.
And the further away you move, the less counts you're going to get. The closer you move, the more counts. So we standardized that for each trial that we conducted. So just because it seems a little bit foreign, this is our roles that we played in the research. Steve was the man on the computer here. He had his watch and he was conducting time as well, because if you guys aren't familiar with radioactive nuclides, they decay, so they become less radioactive over time. So we had to do different decay equations to figure out what the actual activity was at the beginning of each trial. So Steve was recording times in trial so that we could do decay factors on those. This was our pet pig right here. This is the graphene aerogel sitting on top of that. What my duty was to switch out the materials so that we can get those 1-minute images. Steve was recording the start of each trial so that our results were validated so that we could get proper decay equations.
Okay, some results. So we used 2 different radionuclides. For the reason that these are the most common ones that we use, and they both decay. So this is our F18. It has a faster decay rate, and we were able to graph that it was in fact decaying. Next. And then we had technetium-99, and once again we were able to demonstrate that it did decay over a time of minutes from many counts to lower counts.
So this is exactly what we expected to happen. Decay, or radioactive nuclide decay, is a linear pattern. So when we plotted out our results, we got a linear graph, thus verifying that we were decaying properly. Some more results that we had here. So based on the counts and the time elapsed, we were able to guesstimate how many counts we would have. And we compared that to the actual amount of counts we had. So you can see here trial 1 through 7, the counts predicted versus the actual are the same, if not varied by just a little bit. That was the same thing for the graphene using Tech99M. What we did was we actually drew a little region of interest in the center of the screen, and that region of interest picked up a certain amount of counts. The pixels on the region of interest was the same for every single trial. What we did is copied and pasted it, thus verifying the results as well.
This didn't show up so large on our screen here. It just says that our results, our percent error, were very small. When we were counting some counts, we were talking in the neighborhood of 500,000 counts. And some of these we were only off by 2 or 3 counts. So a very good margin of error on our research.
So up until this point, you can basically tell that we were trying to validate our research results, because the whole goal of this research was to put an attenuation coefficient to graphene aerogel, which has not ever been put to the material before. So our reference was the Morphin's Handbook of Reference Data for Non-Destructive Testing. So we used the materials aluminum, carbon, copper, lead, and tungsten. These were the attenuation coefficients assigned by Morphin's, and they were actually the same, if not a few percentages off from the ones that we received. So we were able to validate our results, saying that they lined up with the attenuation coefficients that is standard for the field. So that being said, we were able to accurately choose an attenuation coefficient for graphene aerogel, which was 0.015.
You want to leave that up too? So if I'm an architect, I'm building a room, and I need to lead line the walls, they would go to this table. Or if I'm building a safety vest for somebody, and you would go to this table and say, listen, lead does a great job where aluminum doesn't. That's why you have lead-lined vests. So what did we find out? The graphs validated our results. We also found out that if the patterns of graphene were very similar to carbon, because it is a carbon-based compound. We also found out that it doesn't attenuate very well. Yes.
So we'll go into that right now.
Okay, sorry.
So the conclusion of that, at the current price, graphene is $323 a gram, so it's a very expensive material. Due to the cost, the application is limited to research and future applications if they're able to bring that price down. Given the low attenuation properties, though, it could actually be applicable in PET. We were thinking to use it as a shielding material. Instead, it could actually be used as patient restraints or a positioning system for PET brain studies. Nuclear medicine scans are easily affected by motion. So with the different disorders some of these patients have, it's a little bit difficult to stand still sometimes. So we use little wedges that can be used on either side. Depending on the material, you're going to see the wedges. So that graphene aerogel with its low attenuation properties won't show up on there, thus giving a better diagnostic scan. We could also use it in graphene pillows as head holders, or the patient imaging table or bed. The patient imaging table, especially now, it's an issue with weight. These patients keep getting bigger, and the weight limit on these relatively stays the same. Like Steve mentioned, it's a really, really strong material. So if that price can be lowered, there's application for it to be used in the bed to be able to scan heavier patients.
And they could also retrofit the beds. The current capacity is at 350 pounds. This could make it a 2-ton limit.
So finally, our acknowledgements. We would like to thank the following individuals for assisting us in our research. Dr. Frank DiFilippo, he was the physicist at the Cleveland Clinic, and our professors, Mrs. Donna Mason, Dr. William Wetling, and Dr. Angela Macy-Byers. Without them, we wouldn't have been able to conduct the research that we have. Here are our references. Thank you for your attention, everyone. Do we have any questions?